When Getting Gassed Isn't Ideal Part 2 is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. These two videos, When Getting Gassed Isn't Ideal Part 1 and Part 2, are discussions of what to do when PV doesn't equal nRT. Part 1 discusses generalized compressibility, the virial equation, and the Soave-Redlich-Kwong equation. Part 2 does a set of example calculations. As discussed in Part 1, the ideal gas equation of state is inaccurate at high pressures and low temperatures. In these cases, the PV-T relationship is more complex. We can categorize the non-ideality of the gas with compressibility, Z. It is defined as PV hat over RT. For an ideal gas, the compressibility is 1, so the further Z is from 1, the less ideal the gas's behavior is. Z can be greater than or less than 1. Real gases are, to a large degree, characterized by the critical parameters, the critical temperature, Tc, and the critical pressure, Pc. They are determined experimentally and also by data fitting large sets of PVT data. Real gas calculations are typically performed in one of two ways, either graphically with the generalized compressibility charts or with equations of state. The generalized compressibility charts are good for quick calculations and estimations, but with the growth of readily available computing resources, they rarely find use outside the classroom. Almost everything these days is done with equations of state. There is a family of equations based on the virial equation of state, which is basically a series expansion in terms of the reciprocal of the molar volume. They tend to be fairly mathematically complex. There is also a large family of equations of state that are cubic in the molar volume. We have looked at the Soave modification of the Redlich-Kwong equation of state, and we'll look in the next video at the Peng-Robinson equation of state. There are also less common equations of state. Let's work an example. Let's say that we have a stream of propane at 423 Kelvin and 70 atmospheres flowing at a rate of 100 kmols per hour. We want to estimate the volumetric flow rate using the ideal gas law, the generalized compressibility chart, and the Soave-Redlich-Kwong equation, and compare the results with the results for the experimental molar volume of propane at these conditions of 0.2579 liters per mole. First, from Table 1 in the Part 1 video, we get Tc is 370 K and Pc is 4.23 megapascals. Then, from the link on the website, we get that the acentric factor for propane is 0.153. We have to start with the ideal gas law because some of the other methods only give us Z, not V hat, so we'll need V hat ideal gas for those other calculations. V hat ideal gas is just RT over P in both the SI units of meters cubed per mole and in liters per mole. Then the volumetric flow rate is just the molar flow rate times the molar volume, giving almost 50 cubic meters per hour. At this point, we can calculate the empirical compressibility as the experimental molar volume over the ideal gas one, giving 0.5210. The empirical flow rate is then Z times the ideal gas flow rate, or almost 26 cubic meters per hour. Now for the generalized compressibility chart, we have to calculate the reduced pressure is 1.677, and the reduced temperature is 1.143. We then draw a line up from PR equals 1.677 to the TR equals 1.143 curve. Then we draw a line over to Z and read off 0.5139. I'm quite certain that you can read this graph to support significant figures, right? Okay, so I cheated a little. This graph was generated from the Lee-Kessler equation of state, and I have a spreadsheet that has the Lee-Kessler equation of state on it, so I used it to calculate the value that I would have gotten if I could read the graph that well. Lee-Kessler takes too long to explain, so we're just going to use the graph, except for me. Finally, the generalized correlations flow rate is Z times V hat ideal gas, or just above 25 cubic meters per hour. Now for SRK. I haven't put units down for A, B, or alpha because I know that if my pressures, temperatures, and specific volumes are in SI units, pascals, Kelvin, and meters cubed per mole, everything will work out. However, it might be good practice to ask what the units are. Alpha and M are easy. A works out to be 0.9564, B is 6.301 times 10 to the negative 5, M is 0.7188, and alpha is 0.9030. I then have to arrange the SRK as a function of V hat that will be 0 when V hat is a root, as discussed in the Solving Nonlinear Equations with the Spreadsheet video. I programmed the whole thing into a spreadsheet, which is on the website, with the link in the video description if you want to take a look, and force f of V hat to 0 by varying V hat using goal seek. The result is that V hat equals 2.878 times 10 to the negative 4th meters cubed per mole. Z is 0.5804. And V.SRK is just under 29 cubic meters per hour. So how did we do? We have here a table for the actual or measured values, ideal gas, generalized compressibility, and SRK. Ideal gas is almost twice the correct value, so it's no good at 70 atmospheres for propane. The generalized correlation is less than 1% off, which happens to be luck, not a general trend, and SRK is just under 12% off, which is a vast improvement over ideal gas. Why didn't I use the truncated virial equation? Go check the limits on its accuracy, and then you tell me. As I said, the spreadsheet is linked on the website. Here is the image from it, showing how I laid it out and what it actually calculated. The goal-seek parameters are indicated by vary in goal-seek and set to 0. Parts 1 and 2 give you a very good introduction to methods for working with real gases. We still have to do mixtures of real gases. The next level of working with real gases and mixtures of real gases is to do phase and chemical reaction engineering with them. We will save those for the advanced videos. The takeaways from this video are: 1. Real gases are characterized by at least 2 experimental parameters, PC and TC. 2. When a third parameter is needed for greater accuracy, the acentric factor, omega, is used. 3. Real gas properties can be characterized graphically with the generalized compressibility charts. 4. Real gas properties can also be characterized by equations of state, such as the Varial equation and the Soave-Redlich-Kwong equation. Thanks for watching. This video was brought to you by the DOFPro team.